Kia ora, Year 12 and 13. This is question 1, part D and E from the 2015 Complex Numbers paper. So the first part here is a merit question and the second part is an excellence question. Right, the first one, part D, prove that the roots of this equation, which is just a wee quadratic, are always real for all values of c, where c is real. Right, so you might be tempted to think, okay, roots of the equation, I have to find the roots of the equation. So you're going to start thinking like this: x is equal to negative b plus or minus da 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 over 2a. But we don't have to do that, because all we're asked to prove is that the roots are always real for all values of c. So to prove that the roots are real, we just have to work with the discriminant in here. Okay, so I'll just change the pen back. So what we need to show is that b squared minus 4ac is greater than or equal to 0. Now I'm saying greater than or equal to there because I don't have to prove that there are two roots. So that would be a strict inequality if that were required, but it's not. So we're going to go ahead and do my a, b and c as usual. So a is 3, b is equal to 2c plus 1, and c, slightly confusingly, c is equal to negative c plus 3. So those c's obviously mean different things. So now we're going to find out b squared minus 4ac is equal to 2c plus 1 squared minus 4 times 3 times negative c plus 3. Right, I'll pop in a new slide and we'll expand that out and simplify. So that equals 2c plus 1 squared plus 12 times c plus 3. So let's expand and we get 4c squared plus 4c plus 1 plus 12c plus 36, which equals 4c squared plus 16c plus 37. So if I'm looking to show that something's positive, then a nice way to do it is to find that it's equal to something squared, and then maybe we're going to have a leftover bit. So that's what we're going to do here. We're going to do completing the square on this bit here. Right, so this is equal to 4 times c squared plus 4c plus 37. So let's complete the square on this. We get c plus 2 squared. Now, what I've got when I work that back is that I've added in a plus 4. Right, so this is what I'm completing this. I've added in a plus 4 times 4, so I've added in 16. Right, so I need to take out 16 to keep that all the same. Okay, so just again, what we've got here is we've got that expression, and we've rewritten that expression as this. And that should say 37, not 31. Right, so what I've got now is I've got 4 times c plus 2 squared plus 21. Right, I should be really happy now. This is going to be strictly greater than 0 because 4 times c plus 2 squared is going to be greater than or equal to 0, and 21 is greater than 0. Okay, so that's all we have to do for that one. Right, on to part E. So that was a merit question, and once you've seen that technique, it's quite an easy one to apply if you're looking to show that you've got real roots. Okay, so completing the square will always have you end up with the first part of the expression being positive, and then if you've got the leftover bit positive as well, the whole thing will be positive. Right, now this question has got two ways to do it, and one of them is way easier than the other. So I'm going to do the mucky way first. If x squared plus bx plus c and x squared plus dx plus e, so two different quadratics, have got a common factor of x minus p, then we have to prove this, which is talking about the relationship between the coefficients, right? So what do we know? If we know x minus p is a factor and it's a quadratic, then we can start by saying this. We can write out x squared plus bx plus c in factorised form. So it's going to have an x minus p, and then it's going to have a something else. right? And we'll call that something else x minus q. Now, you could pick different letters here, obviously, it doesn't matter, but I've done the ones that match up with what's in the assessment schedule, just because some of you will have that printed out while you're working through these. Okay, so let's assume that that's the case, and then let's do the same thing for the other quadratic. So we know that x squared plus dx plus e also has x minus p as a factor, and it's going to be times something else. So we'll make that be times x minus r. Right, it doesn't matter that we're saying minus here instead of plus, because q could be a negative number, right? So there's no problem with doing that. Now, if we expand out both sides, we can match up some coefficients. So the first one, we're going to have x squared plus bx plus c is equal to x squared minus px minus qx plus pq. Right, and you can see I'm going to be doing some matching up with these and with this and those, but not quite yet. Same thing on the next line, x squared plus dx plus e is equal to x squared minus px minus rx plus pr. Now, I did say this was the yucky way, just in case you're sitting out there groaning. Right, so what does that give me? Well, what can we say about b? Well, b has to be the same as that coefficient there. So we get b is equal to negative p minus q. What about c? Well, c here has to match up here, so c must equal pq. In the next one, we'll just change pen colour, we'll go for purple. D has got to, so d of x has got to match up here. So we get d is equal to negative p minus r, and e has to match up to pr. Right, and now we're going to prove that this equals this. So we're going to go back to this expression and we're going to substitute b, c, d and e, and we're going to hope that p pops out the other end. So I'm going to do that on a new slide. Right, so we've got e minus c over b minus d. I'm hoping you wrote those down as you went on the last page. So e minus c is going to be pr minus pq. B minus d, well, b was negative p minus q, minus d was negative p minus r. Right, so the numerator we can write like this, p times r minus q. The denominator gives me negative p minus q plus p plus r. So that's p times r minus q over r minus q, which equals p. Happy face. Right, so we get there, but it is quite a mess, and you know that you're going to be under massive time pressure if you're doing all three papers. So we'd like to think of a nicer way, if we can. So I'm going to do that on the next slide. Okay, we're told, I'll just write the question out again. We've got x squared plus bx plus c, and we've got x squared plus dx plus e, and they both have a common factor of x minus p. So what we know from the factor theorem is that if x minus p is a factor, then if I evaluate with x equals to p, I will get 0. Okay? So what I can do now is I'm going to substitute in p into each of those expressions. And because x minus p is a factor, I know that p squared plus bp plus c equals 0. Right? That's what it means for something to be a factor. The other one, I can do the same thing because x minus p is a factor of that one too. So p squared plus dp plus e equals 0. But if they're both 0, then they're the same. So we can equate those two things. We get p squared plus bp plus c is equal to p squared plus dp plus e. Right, and look at that. The p squareds go, and we can collect up things with p in them. So we're going to have bp minus dp is equal to e minus c. Now I'm running out of space, so I'm going to go up here. So taking out the common factor of p, I get p times b minus d is equal to e minus c. So p is equal to e minus c over b minus d, as required. Okay, so much less algebra intensive way to do that question. Okay, hope you enjoyed that. Thanks for watching, and I'll be back with question 2 shortly.